Okay, so we looked at the first derivative test, concavity, points of inflection in the second derivative test. Notes the other day, we started examples with the first derivative test, so we're down to examples for the concavity test now. So starting with number 8. Use the concavity test to determine the intervals on which the graph of the function is A concave up and B concave down. So number 8 is y is equal to negative x to the 4th plus 4x cubed minus 4x plus 1. Alright, so we're going to take two derivatives. So what is the first derivative of this? Yep. And then for concavity, we need the second derivative to help us determine where it's concave up and down. So what would the second derivative be?
Negative 12x squared plus 4x.
So then now we're gonna factor this out and find the zeros. So we set this equal to 0. I'm gonna take out it doesn't really matter where the negative goes. I'm gonna take out the negative 12 and an x. That leaves me with x plus 2. Or wait, x minus 2, not plus 2. Set that equal to 0. So negative 12x equals 0. And then x minus 2 equals 0. So x equals 0, or x is equal to 2. So then we're doing 0 and 2, and we're doing this. The sign of these is going into the second derivative. Okay, so we're plugging the values into the y double prime equation here. So if I put in negative 1, is the result positive or negative? Negative. Between 0 and 2, so if I plug in 1 to the second derivative, is it positive or negative?
Negative.
1? Yeah, positive. And then over here, if I plug in something like 3, it'd be negative. What?
The pigs are really obstructing.
I know, it's very difficult to see. Okay. So we're concave up from 0 to 2, okay, because that's the region where it's positive. So from 0 to 2, and these are open intervals. And then we're concave down in the regions where it is negative. So from negative infinity to 0, and from 2 to infinity, it's concave down.
Can we go to the office really fast? I was taking a note over there. If I can find it.
Oh boy, I better sit back down. We're gonna be here for a while.
All right, 12.
Can you show motion?
y is equal to e to the x for 0 less than or equal to x less than or equal to 2 pi. Interesting. So what is the first derivative of this? E to the x, and then how about the second derivative? E to the x. So then the question would be, okay, if I set this equal to 0, okay, to find the zeros or whatever, I would have I would end up with e. Why is that doing that? Hold on. Let me rephrase. Is there any way for this to be negative? No. So what does that mean? It's got to be concave what? If it's always positive. Concave up. So y double prime is always positive. Okay, obviously y prime is as well. So since that's always positive, it's got to be concave up. Let's do 10 so we get another one that actually will have a sign chart with it. 10, y is equal to 5 minus x to the 1/3. So first derivative. You in your car?
Okay.
Negative 1/3 x.
You said to the negative 2/3, right? Okay. The door was shutting, so I was like not 100% sure if that's what you said. All right, so that's the first derivative. How about the second derivative? All right, so then making a sign chart. Why is this pencil freezing? Come on. Or well, I guess I need to find where it's equal to 0 first. So set this equal to 0. So I would have x to the negative 5/3 is equal to 0 because that 2/9 is going away. So what does x have to be equal to be 0? Zero. So I'm going to check 0. Again, I'm checking this for y double prime. So if I plug in -1, what happens to my answer? It's negative. And then if I plug in 1, it's positive. So we are concave down from -infinity to 0, and concave up from 0 to infinity. Alright, so then points of inflection are the next one. So it says find all points of inflection for the given problem. So 16, y is equal to x cubed times 4 minus x. So there's a couple ways you could technically do this. If you wanted to do a product rule for the derivative, you could, or we could distribute first and then just take the derivative, and it would probably make life a little bit easier. So I always like the easy route. So I would rewrite this as y is equal to 4x cubed minus x to the 4th. And I need to get down to the second derivative to find my zeros. So what would my first derivative be?
12x squared minus 4x.
And so then second derivative would be what?
24x minus 12x squared.
So then I can take something out of both pieces. So I'll take out a 12x, I guess. So 12x leaves me with 2 minus x. Yeah. So then 12x is equal to 0, or 2 minus x is equal to 0. So I have the x is equal to 0, or I'll have that x is equal to 2. We take these and we plug these back into the original, because we're trying to find what the actual point of inflection is, so we need the xy point for that. So if I plug 0 into the original equation, what do I get?
0.
So at 0, it's 0. And the other one, if I plug 2 into the original equation, what do I get? When you plug 2 in, 4 minus 2 is 2, 2 times 2 cubed, so 8 times 2 is 16. So then the other point is 216. All right, which one of these do I want to do first? Let's go ahead and do 28, and then I'll come back to that. All right, so 28 says, a particle is moving along the x-axis with a position function x of t. Find the velocity and acceleration and describe the motion of the particle for t greater than or equal to 0. So basically, I want to know where it's increasing and decreasing, and then where it's accelerating or decelerating, okay? And so those things will line up with if it's moving right, it's increasing. If it's left, it's decreasing. If it's concave up, it's accelerating. And if it's concave down, it's decelerating. All right, so 28 tells us that our position function is x of t equal to 3t squared minus 2t cubed. So if I want to get velocity, what do I need to do? It's been a while since we've done one like this. First derivative, so what would that be? Yep. So then now what I want to do is I want to initially I'm looking for if it's right or right or left, meaning increasing or decreasing. Okay, and that's going to be the other thing is if it's right, it's positive. If it's left, it's negative. I feel like that probably just kind of generally makes sense, but sometimes they do things backwards. So this is the first thing that we're doing. So we're doing this in relation to this one. So I'm going to find the zeros and I'm going to make a sign chart for them. So take out a 6t, I'm left with 1 minus t equal to 0. So I'm going to have t is equal to 0 and t is equal to 1. Now, these problems, I'm very specifically dealing with a particle moving as a function of time. So can time ever be negative? So I can never go to the left of the 0. So if 0 wasn't one of my zeros, if you will, I would still stop at 0 because I can't have negative time. Okay, so I'm not going to be worrying about negative infinity to 0 area. I'm just worried about what happens beyond 0. So when I set up my chart, I'm going to have 0 and 1. So if I were to use, like, let's say 1/2, what do I have?
You're putting this into the original?
Yes. Yes, into the original. Or, well, wait a second. Hold on. I actually think it's this, so I think it's actually going into the first derivative. So that was a good question. I wasn't paying attention. That's why I typically like to put what I'm putting it into, because I'll forget.
I got 3 minus 6 fourths.
So it's positive. Oops, wrong color. And then if I were to use like 2, what do I have? Negative. So it's positive here, so that means that it's increasing and it's going right. And then on the other one, it's negative, so it's decreasing. We're going left. Let me see how they officially want the answers written for these. This 5.3, I think. What is this, number 28? Oh, okay. We're going to answer the questions in part C, so just leave it there for the moment. This was part A. Okay, so then part B, I'll switch colors. All right, so part B then wants where it's accelerating. Or, well, I guess technically part A just is asking for the velocity, so really all part A was asking for is this right here, but we need this to answer part C, so that's why I went ahead and did it. So what would the derivative of velocity be to give us acceleration?
Six
12t. So then if I set that equal to 0, that's just going to give me, what, positive 1/2. And again, same thing, I can't go below 0, so when I do my sign chart, and this is going to go into the second derivative because we're dealing with concavity to determine if it is accelerating or decelerating. So just like we use the second derivative up here for concavity, we're going to do the same thing down here with the acceleration. So we have 0, and then we have 1/2. So I would just try something like 1/4 because that's going to be nice to cancel there. Positive. And then over here, if I tried like 1, it's going to be negative. So that means in this region, it's concave up, which means that it is accelerating. Over here, since it's negative, it's concave down, meaning it is decelerating. Okay, so again, technically part B just wants this. Part C officially says, describe the motion of the particle for t greater than or equal to 0. Okay, they're just saying so as long as you actually have time. As far as what they want, basically they're just saying that it begins at position 0. It's moving in the positive direction till it reaches 1. When t equals 1, then it changes direction. It moves in the negative direction thereafter. If you had worked this and this here, that would be sufficient to answer question C for me if you were to be doing it, okay? If it actually asked you on like the AP test to explain this, then I would basically just take your information and write in words where it's accelerating, decelerating, and where it's moving left and right, meaning it's increasing and decreasing there. So that stuff would be sufficient for part C for me. So let's do this, and we'll just put that that's part C. Okay, so then the last thing in this section, and then what I'm going to do is tomorrow give you guys time to work on the problems, so that way you don't have to do anything over the long weekend. Tuesday we'll review 5.1 to 5.3 stuff, and then Wednesday we'll have a quiz, and then we'll start 5.4 after that. So, okay. So these second derivative test problems are kind of long. So if we need to see more than one, I can do more than one, but I'm picking like one of the hardest ones in here. So hopefully it'll not be too bad. So this is the second derivative test problem. So let's use the second derivative test to find the local extrema for the function. So 36 is y is equal to 3x to the fifth minus 25x cubed plus 60x plus 20. So what I need to do first is I need to find the first derivative, and then what I want to do is I want to find where the first derivative is equal to 0. Then I take the second derivative of the function and then I evaluate the second derivative at the points that we found from the first derivative. Okay, so I know that probably sounds confusing. I just want you to kind of know what we're getting ready to get ourselves into when we start this. So, first derivative is what?
15x to the 4 minus 75x squared plus 60.
Do you notice anything in common between all of these numbers? 15, so I can take a 15 out. I'm setting it equal to 0, so the 15 is actually going to go away. So if I take the 15, x to the fourth minus that 5x squared plus 4. So 15 is going to go away because of that. So then I want to factor this. I'm going to show you a trick for factoring something like this for the event that it's not super easy to factor or you may not see exactly what's going on. It's called U-Substitution. It'll come in handy, or you'll hear U-Substitution more in a different context later, but I'm going to say let u be equal to x squared. And I'm actually going to rewrite this function here in terms of u's. So I'm going to have u squared minus 5u plus 4. And I'm still going to have that being equal to 0. I want to factor this, so what would this factor into? So I need, yeah. So x minus 4, x minus 1, or I guess I should actually say u, because I don't want to confuse that. So then, now that I factored it, I've made my life a little bit easier, I'm going to plug the x squared back in. So I'm going to have x squared minus 4 times x squared minus 1 equals 0. Now I'm going to split it. So x squared minus 4 equals 0. X squared minus 1 equals 0. So if I move this over, x squared is equal to 4. Take the square root. That gives me that x is equal to positive or negative 2. And then over here, x squared is equal to 1. So then x is equal to plus or minus 1. So these values here, these 4 values, are going to get plugged into the second derivative. And then if that value ends up being greater than 0, it's going to be a min. If it's less than 0, it's going to be a max. So I need the second derivative now of y. I'll try to leave that sitting there for a second. So let's see, find a different color. Purple. So what would the second derivative be? Alright, so then I now have that. So I'm going to evaluate this function at each of these four values. So I can actually go ahead and set them all up. So f double prime of -2, f double prime of 2, f double prime of -1, and then f double prime of 1. So then I'm going to take and I'm going to plug in these values. So I'm going to have 60 times -2 cubed minus 150 times -2 for the first one. Second one, 60 times 2 cubed minus 150 times 2. Next one, I'm going to have 60 times -1 cubed minus 150 times -1. And then the last one, 60 times 1 cubed minus 150 times 1. And then I just want to see what each of these are equal to. So -2 cubed is -8 times 60. That's going to give me 480, -480. And then -150 times -2 is going to be positive 300. So then this one, -480 plus 300 gives me -180. For the second one, 2 cubed is 8 times 60 is just going to be positive 480 this time. Then minus 150 times 2 is going to be minus 300. So this one is going to be positive 180. The next one, the -1 cubed is just -1, so that's going to give me -60. The -150 times -1 is going to be plus 150. So that's going to give me 90. And then 60 times 1 cubed is going to be 60. 150 times -150 times 1 is minus 150. So that one's going to be -90. So from the second derivative test, it says that if we take the first derivative and set it equal to 0, and then we evaluate the second derivative at that value. If it's less than 0, it's a max at that value, and if it's greater than 0, it's a min at that value. So this first one is less than 0, second one is greater than 0, third one is greater than 0, fourth one is less than 0. So we can say for the first one, therefore, f has a local max at x equals -2. The next one is greater than 0. We can say therefore, f has a local min at x equals 2. So the next one's also greater than. We can say therefore f has a local min at x equals -1. And then the last one is less than, so it's a max. So therefore f has a local max at x is equal to 1. And if you wanted to like write them all like in their own thing. Like say f has a local min at x is equal to 2 and at x is equal to -1, just to make writing shorter. If you were like doing the problem like on a test or something, that would be fine. Any questions about any of these? Okay, so then the problems that I would recommend that you look at, and tomorrow you'll have time to do them, like I said. Be 1, 3, 7, 13, 17, which is probably one that's a little bit harder, but I would still recommend you look at it. And then 25, 27, and then 33 and 35.